Welcome back to our channel, where today we dive deep into a groundbreaking development in the world of physics. The James Webb Space Telescope, JWST, has delivered observations that challenge the very foundations of the standard model of particle physics, prompting scientists around the world to rethink some core concepts of cosmology. Join us as we explore what this means for the future of science and how our understanding of the universe is set to change. In 1929, Edwin Hubble catapulted the world of astronomy into a new era with a stunning revelation: the universe was not ageless but had a definite beginning. Utilizing the era's most sophisticated telescope, Hubble made a pivotal observation. He noticed that distant galaxies were retreating from us at speeds proportional to their distance, suggesting that the universe was not only expanding but doing so uniformly in every direction. This expansion, quantified by what is now known as the Hubble constant, offered a potential method to calculate the age of the universe by rewinding the cosmic clock. However, pinning down the Hubble constant has proven to be an immensely challenging task for astronomers. Over the years, scientists have employed various techniques to measure this expansion rate. One approach involves studying nearby supernovae, while another examines the cosmic microwave background radiation, a relic from the universe's infancy, shortly after the Big Bang. These observations, particularly those related to the cosmic microwave background, indicate a specific rate at which the universe should be expanding today. Yet, reconciling these findings with other measurements has been notoriously difficult, often described as a significant and persistent puzzle in cosmology. In the realm of cosmology, a dramatic puzzle is unfolding. Two predominant methods of measuring the universe's expansion rate offer conflicting results. One suggests an expansion rate of about 67.8 km per second per megaparsec, while the other estimates it at 73.2 km per second per megaparsec. This discrepancy, which hovers around 10%, has sparked intense debate among physicists and astronomers. If both measurements are accurate, it implies a fundamental gap in our understanding of the universe's composition, a situation now referred to as the crisis in cosmology. To tackle this enigma, scientists turned to the venerable Hubble Space Telescope, hoping it could provide a definitive expansion rate. However, the findings revealed that the universe might be expanding at different rates in different regions, further complicating the issue. The plot thickened dramatically with the involvement of humanity's most advanced observatory, the James Webb Space Telescope. Tasked with double-checking the Hubble's findings, the James Webb Telescope's observations not only deepened the so-called Hubble tension, but also dismissed the likelihood of mere calculation errors. This development throws open the proverbial Pandora's box of cosmology. The implications are profound. The universe might not exhibit uniformity in all directions, challenging a core tenet of modern cosmology and potentially triggering a domino effect in our understanding of the cosmos. The standard model of cosmology, which has framed our understanding of the Big Bang and the universe's evolution over the past 13.7 billion years, is now on unsteady ground. This shift isn't just a matter of academic debate. Top astronomers worldwide are taking it seriously. A high-level meeting is set to convene at London's Royal Society, bringing together leading minds to rigorously examine the standard model and reassess our grasp of the cosmos. Co-organizer and Oxford cosmologist, UIA Sar, remarked that our current cosmological model, crafted in 1922, is showing its age. Increasingly, respected voices within the community are echoing this sentiment, he said. Adding to the complexity, recent observations by the James Webb Telescope have introduced startling revelations. Scientists have detected variances in the rate at which different parts of the universe are expanding, hinting at the possible influence of cosmic megastructures on the universe's growth. Moreover, the James Webb Telescope has spotted several thousand quasars, revealing a potential asymmetry in the universe. One hemisphere appears to contain a higher concentration of quasars, suggesting an uneven distribution of mass across the cosmic expanse. These findings challenge long-standing views and hint at a more intricate cosmic landscape than previously imagined. The enigmatic force known as dark energy, theorized to drive the universe's accelerated expansion, might be more elusive than ever. It would mean that 2/3 of the universe has just vanished, remarked Saka during a pivotal scientific gathering. Professor Wendy Fredman, sharing new insights from the James Webb Space Telescope, echoed a sentiment of mystery and necessity for deeper inquiry. We're seeing all these intriguing clues, each with varying degrees of significance. It's crucial to delve further into the points where our standard model might falter. I'm not convinced we've found something enduring yet, she noted. In a related development, Alexia Lopez, a PhD student at the University of Central Lancashire, has identified what could be groundbreaking cosmic megastructures, intriguingly named the Big Ring and the Giant Arc. These formations, outlined by galaxies and galaxy clusters, stretch across scales that defy the expected uniform smoothness of the universe. Astronomers at the University of Central Lancashire recently unveiled one such astonishing structure. Known as the Big Ring, this vast formation spans a breathtaking 1.3 billion light-years in diameter. Its sheer size presents a formidable challenge to our current cosmological theories. Yes, this monumental structure signals that our universe might be far more textured and complex than previously imagined. The discovery of a massive cosmic structure, defying all odds and expectations, has thrown a wrench into the gears of cosmological theory. Dubbed the Big Ring, this colossal aggregation of matter, located about 9.2 billion light-years from Earth near the handle of the Big Dipper, is invisible to the naked eye and so faint that uncovering it demanded extensive time and computational resources. Researchers unraveled the Big Ring's existence by examining the light from quasars, extremely bright and distant celestial objects. They measured how this light was absorbed as it passed through interstellar space, a technique that revealed the amount of mass in these vast cosmic stretches. Alongside the Big Ring, scientists also identified another vast structure known as the Giant Arc. These findings pose a significant challenge to a fundamental assumption in astronomy, the cosmological principle, which posits that the universe should appear uniform and isotropic at large scales, meaning matter should be evenly distributed across the cosmos. The existence of such immense structures like the Big Ring and Giant Arc suggests that, in practice, this may not be the case, prompting a major re-evaluation of our understanding of the universe's structure. In the cosmic expanse of the universe, governed by the lambda-cold dark matter model, the cosmological principle asserts that matter should appear uniformly distributed across a vast scale, up to about 1.2 billion light-years. However, the Big Ring, sprawling even beyond this boundary, poses a direct challenge to this model. But the plot thickens. The Big Ring is not alone in its defiance. Enter the Claus-Campusano quasar group, discovered in 1991. This cluster of 34 quasars spans a staggering 2 billion light-years. Yet, even this pales in comparison to the large quasar group, which stretches over 4 billion light-years, well beyond the supposed uniformity cutoff. Further complicating the picture is the Great Arc, extending 3.3 billion light-years, and its neighbor, the newly identified Big Ring. But dwarfing them all is the Hercules Corona Borealis Great Wall, a supercluster of galaxies that measures about 10 billion light-years across. Could these immense structures merely be cosmic coincidences, or do they signal a fundamental misunderstanding in our grasp of the universe's structure? Each new discovery not only captivates the imagination but also challenges the bedrock principles of cosmology. The enigmatic Big Ring stands out with a statistical significance of 5.2 sigma, indicating that its formation by mere chance is exceedingly unlikely, with odds less than 1 in 3 million. This staggering revelation has left astronomers and physicists grappling with the implications. Clearly, our existing models need a serious overhaul. Professor Don Poo from the University of Warwick voices a common sentiment: it's incredibly difficult to imagine any natural process capable of creating these colossal structures. Consequently, some theorists suggest that these might be relics from the early universe, imprints of high and low-density material frozen into the extragalactic medium. Yet, the pressing question remains: how were such massive structures formed? I invite you to share your thoughts in the comments below. Meanwhile, this puzzle is just one of many confronting our understanding of the cosmos. More than 2 years after the triumphant launch of the James Webb Space Telescope, astronomers are reveling in a golden era of discovery, as the telescope continually expands the boundaries of our cosmic vision. However, these discoveries have also unleashed a Pandora's box of challenges for cosmologists, especially as recent observations probe the universe's conditions within the first 500 million years post-Big Bang. In the vast expanse of space and time, the James Webb Space Telescope has made an astonishing observation. It spotted galaxies that are anything but juvenile, appearing unexpectedly massive and mature, challenging our assumptions about the early universe. Among these, astronomers are now focusing on a galaxy that could be one of the oldest observed, a cosmic behemoth already brimming with billions of stars. Just 2 years ago, this galaxy was merely an unusual speck of light in the Hubble Space Telescope's field of view. At the time, scientists had no idea that this faint glow was actually a colossal galaxy lurking at the dawn of time. It wasn't until the James Webb Space Telescope turned its gaze upon this speck that its true nature was revealed, a primordial galaxy, significantly more massive and developed than any models had predicted. Dubbed GZ9P3, this galaxy is observed at a redshift of Z equals 9.3, which means we are seeing it as it existed just 510 million years after the Big Bang. To put this in perspective, we've observed other galaxies dating back to about 3,500 million years post-Big Bang, but none possess the sheer mass of GZ9P3. This discovery suggests that star formation within this galaxy occurred much more rapidly and efficiently than previously thought, enabling it to reach its impressive size and maturity at such an early cosmic epoch. But there's more to GZ9P3 than just its size. This ancient galaxy also sports a peculiar shape that may hold clues to the early universe's secrets. Researchers have discovered that GZ9P3 features 2 bright patches within its structure, indicating dual dense nuclei. This compelling evidence strongly suggests a galactic merger, 2 primordial galaxies colliding in the youthful cosmos, a dramatic event that likely shaped this galaxy's destiny. The team didn't stop at identifying the age, mass, and shape of this ancient galaxy, they delved deeper into its stellar composition. They found that young, bright stars dominate the galaxy's visage. Utilizing the James Webb Space Telescope, JWST, the researchers detected specific elements such as silicon, carbon, and iron within the older stars of GZ9P3. Iron is the heaviest element that stars can synthesize. When these stars met their explosive ends, they scattered these elements into space, seeding the early universe with metals that would eventually contribute to the formation of new stars. Moreover, the team was surprised to find a larger-than-expected number of old stars in GZ9P3. This indicates that the galaxy may have reached chemical maturity much sooner than anticipated, with its stars contributing metals to the cosmos at a faster rate than previously thought. The presence of an unexpectedly mature older star population in GZ9P3 not only adds a new layer of complexity but also challenges our current understanding of how quickly galaxies evolve and mature. The startling discovery that stars within certain galaxies formed much earlier than previously believed suggests they reached advanced ages by this point in cosmic history. These findings hint that our existing models might not fully capture the swift and complex growth of galaxies into chemically mature states. Moreover, these galaxies are not only surprisingly large, but their formation may also have been significantly influenced by galactic mergers shortly after the Big Bang. This revelation suggests that while our current cosmological framework isn't necessarily incorrect, it likely underestimates the speed and scale of galaxy formation. The fact that these galaxies are more massive than once thought possible adds another layer of complexity to our understanding of the universe's early days. The standard model of particle physics has been the cornerstone of our understanding of the universe's fundamental particles and forces for decades. It explains how everything from galaxies to atoms is held together. However, recent data from the JWST has posed significant questions that this model can't seem to answer, leading to exciting debates and research in the scientific community. Launched with the aim of exploring the cosmos in unprecedented detail, the JWST has exceeded expectations, peering back in time to capture light from the early universe. Its advanced instruments have now gathered data that contradict predictions made by the Standard Model, particularly concerning dark matter and the distribution of galaxies. What does this mean for cosmology? The discrepancies observed suggest that there may be unknown forces at play or that our current understanding of particle physics is incomplete. This revelation has the potential to alter everything from the basics of physics to advanced cosmological theories. The scientific community has reacted with a mix of excitement and urgency. Research teams worldwide are now analyzing the data, with many expecting that this could lead to a new era in theoretical physics. Upcoming experiments and studies are being tailored to explore these anomalies further. As we stand on the brink of potentially revolutionary discoveries, the next few years will be crucial in cosmology. Scientists are preparing for a period of intense study and debate, which will likely result in significant revisions to the Standard Model or perhaps even a completely new framework for understanding the universe. Recent findings from the JWST have brought new questions about dark matter, a mysterious substance that does not emit, absorb, or reflect light but is thought to make up about 27% of the universe. The telescope's observations of galaxy clusters and their gravitational effects suggest properties of dark matter that current theories do not account for, possibly indicating new types of particles or interactions. The Big Bang theory, which describes the universe's explosive birth and subsequent expansion, is another cornerstone of cosmology intertwined with the Standard Model. The JWST's insights into the early universe are providing data that might lead to a refined understanding of the Big Bang, including when and how it happened, challenging long-held assumptions. As cosmologists grapple with these cosmic puzzles, there's also a significant impact on the field of quantum mechanics. The behaviors of particles at incredibly small scales might need re-evaluation. This integration of cosmological and quantum phenomena could lead to a more unified understanding of all forces in the universe. Neutrinos are elusive particles that are incredibly challenging to detect as they rarely interact with matter. Recent data suggests their mass and behavior could be key to understanding the anomalies observed by JWST. This could usher in new technologies and methods for neutrino detection and study, enhancing our grasp of the universe's most hidden aspects. The challenges posed by the JWST's findings are driving technological innovation in astronomy. Future telescopes and instruments are being designed with the capability to observe phenomena that were previously undetectable, setting the stage for further breakthroughs in our understanding of the cosmos. These developments are not just confined to research laboratories, they're also transforming how astrophysics is taught in universities around the world. Curricula are being updated to include these new theories and data, preparing the next generation of physicists to think outside the traditional paradigms. The questions raised by the JWST have encouraged increased collaboration between physicists, chemists, and biologists to explore the life-supporting conditions of distant worlds and the possible biochemistry of extraterrestrial life. This interdisciplinary approach is enriching the scientific community's approach to universal mysteries. There's a growing public interest in cosmology, fueled by these exciting discoveries. More people than ever are engaging with science through educational programs, planetarium shows, and interactive exhibits that explain the implications of JWST's findings and the nature of our universe. The impact of JWST's findings is also felt in the realm of science funding. Governments and private entities are increasingly recognizing the importance of supporting fundamental research that could completely alter our understanding of the universe, leading to increased funding for projects and research initiatives. The detection of gravitational waves has already revolutionized astronomy, and the JWST is poised to add to this revolution by potentially observing effects that could hint at new physics beyond the Standard Model. These observations could provide insights into phenomena like black hole mergers and neutron-star collisions, offering a new layer of understanding of the universe's most violent processes.
Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blisovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.